I'm working with Joop Shea in Leiden and Ben Oppenheimer in Colorado. And so we're working on a project to incorporate a chemical model into hydrodynamic galaxy simulations that will allow us to track the evolution of the abundances of the ions and the molecules of the gas. And so by doing this, we can then calculate the cooling rates of the gas using these non-equilibrium abundances rather than relying on cooling functions that were calculated assuming ionization equilibrium. So one of the main goals of this project will be to look at what impact do these non-equilibrium cooling rates have on the evolution of the galaxy and the structure of the multi-phase ISM within these simulations. So in this talk, I'd just like to show you some of the results we've gotten so far in this project. So in the first half of the talk, I'll introduce the chemical model that we've developed for this project, and I'll show you some of the results where we apply this model but outside of the simulations. So we apply it to gas in a range of different physical conditions that are typical of the diffuse ISM. So we can look at, for example, which species are contributing most to the cooling rate of this gas and what impact the non-equilibrium can have on the cooling rates in certain idealized situations. So for the chemical model, we have a chemical network that includes firstly all of the ionization states of these 11 elements here. So these are the 11 elements that are the most important for the cooling rate. And then we also want to include a handful of molecules as well, because we're particularly interested in the multi-phase ISM. So in the transition is you go from a warm phase around 10 to the 4 Kelvin down to a cold phase of a few hundred Kelvin. So for this we also need to include, for example, H2, CO and so on. So then the chemical network then includes the chemical reactions between these species, so collisional ionization, photoionization, cosmic rays and so on. And also a handful of reactions on dust grains, so in particular the formation of the H2 on dust. So then these reactions give us the rate equations for each species, which we can just integrate. And so once we have the abundances of all these species, we can then calculate the cooling and the heating rates. So again, there are various physical processes involved here, such as metal ion cooling, cooling from molecular hydrogen and so on, and also various heating processes. So there's heating, photoheating and photoelectric dust heating from the UV radiation and heating from the cosmic rays. So the first thing that we can look at is to look at the cooling rates in chemical equilibrium, to look at which species are contributing to the cooling rates. So here we consider gas a range of different densities and temperatures and so on. We then integrate all the chemical abundances until it reaches chemical equilibrium and look at the contribution to total cooling rate from the various species. So I'll show here one example of this. So these are the cooling rates in the presence of the Hartle-McDowell extragalactic UV background and a density of 1 per cubic centimetre. So this is the cooling rate as a function of temperature from 100 to 10 to the 4 Kelvin. So the black curve here is the net cooling rate, and then these coloured curves are the contributions from individual species. So we can see that in this particular example, most of the cooling here is coming from the metals, in particular carbon-2, silicon-2 and iron-2. And then once we go to higher densities, we also see other species such as oxygen-1 and molecular hydrogen also start to become important. So that was in equilibrium, but then we also want to look at what impact can the non-equilibrium have on the cooling rates. So for this we look at certain idealized situations of gas that starts off in chemical equilibrium at either 10 to the 4 or 10 to the 6 Kelvin, and then we allow it to cool either isochorically, so at constant density, or isobarically, so at constant pressure. And then as the gas cools, we evolve the chemical abundances and we compare the cooling rates to what the cooling rate would have been if we simply assumed chemical equilibrium at that temperature. So I'll show here one example of this. This is gas cooling from 10 to the 6 Kelvin and isochorically, so constant density. So I show here the gas density on the y-axis and the temperature on the x-axis. And the colour scale here is showing the log of the ratio of the non-equilibrium cooling rate to the equilibrium cooling rate. So blue regions show where the non-equilibrium suppresses the cooling rate, and red shows where it enhances the cooling rate. So at high temperatures above 10 to the 4 Kelvin, we can see that the non-equilibrium tends to suppress the cooling. And this is due to ionisation lags. So this means that the ions are left in a higher ionisation state than they would be in equilibrium. But these high ionisation states require more energy to be collisionally excited. And so we see that there's less collisional excitation and hence less radiated cooling. So once we go below 10 to the 4 Kelvin, we can see that the direction of this effect actually reverses, and the non-equilibrium actually enhances the cooling rates by up to towards magnitude in this example. And this is because the recombination lags also mean that you have a higher electron abundance than you would have in equilibrium. And so if you have more electrons, this means that you have more collisions between the electrons and ions, and so then you have more collisional excitation and hence more radiative cooling. So below 10 to the 4 Kelvin, it's this effect which becomes most important. So now, for the second half of the talk, I'd like to show you an example of some of the simulations that we're now starting to run, incorporating this chemical model and using these non-equilibrium cooling rates. So for this, we're using the tree SPH code, Gadget 3. In fact, this is using the Eagle version of the code. So it's using many of the subgrid physics models that were developed for the Eagle project, which Rob discussed this morning. For example, we have a thermal supernova feedback, but I'm not including AGN feedback here because we're only looking at dwarf galaxies. So here we're looking at idealized isolated disk galaxies. So we set up a galaxy with an exponential disk of gas and stars, plus a central stellar bulge, all embedded within a dark matter halo. So this example here has a total mass of 10 to the 10 solar masses. We have a resolution of 750 solar masses per gas particle. So then in this video on the right here, you'll see the evolution of the gas in the simulation. So looking at the disk face on and edge on. So we see that at the beginning of the simulation we get a burst of star formation, and the supernovae are blowing these hot bubbles in the disk. So this simulation is actually only run for 200 megayears, so we see that it's only just starting to settle down from the initial conditions by the end of the simulation. So ideally we'll actually need to run these for much longer to get a better feel for the evolution. But for now this at least illustrates how the chemistry is behaving in these simulations. So we want to look at how much of the gas remains within close to chemical equilibrium, and whereabouts is the gas far from equilibrium. So I show this here. So this is for molecular hydrogen, and it's showing as a function of temperature and density. So the colour scale here is showing the ratio of the non-equilibrium H2 abundance that we take from the simulation compared to the H2 abundance that it would have if we assumed chemical equilibrium for each gas particle. So we can see, for example, we have the warm ISM phase here around 10 to the 4 Kelvin. So we can see along the top of the warm ISM phase, we have this red region, so the H2 abundance is higher than equilibrium. And then along the bottom there's a small blue region, so it's lower than equilibrium. One thing to look, so these results are still very preliminary. In particular, this particular simulation, we used just a uniform UV, optically thin UV radiation field. But of course, see the molecular hydrogen in the cold phase and the molecular clouds and so on. You need to include how the gas becomes shielded from the Lyman-Werner radiation. So the next step is that we want to run this, including a prescription for how the gas becomes self-shielded from the UV radiation field. So I'll leave you with the summary. Thank you.
Paula.
I would like to know which chemical network are you using for these simulations, for the reaction rates, from where do you take them?
So for the high ionization states, this is what Jörg and Ben Oppenheimer were doing for the circumgalactic medium. So for that he takes the rate coefficients from cloudy basically, And then we also have, for example, the molecular network is mostly based on Simon Glover's, for example, the CO network. A lot of that's from Simon Glover. So there's a wide range of items.
Another question. In this simulation, do you take into account the chemical enrichment of the gas, and so the parent atoms are changing with time, and so also the chemistry is changing due to the chemical yields from supernovae and etc., or is it?
Yeah. So for example, the metals and so on. So the gas particles do get enriched by the star particles. So the example I showed you, we started it off at 10% stellar metallicity, but subsequently the stars and so on, at the supernova and stellar winds, they do enrich. And so this is done the same way as in the Eagle simulations.
So the chemistry is calculated with this?
Yes, it takes that into account. Yeah.
Right.
So are you following all 157 species in these SPH simulations?
Yeah, so it's following all 157. So, yeah, that's actually one thing we thought of. So obviously in different regions, only a subset of those would be important. So one thing we thought about is, is there a way to automatically make the code sort of reduce the network to only focus on the species that you care about in any given regime? But then there are various overheads and if you want to do that automatically, there are then overheads involved. So it might be possible.
So how much slower is?
What's the price you pay?
So at the moment it slows down the CPU cost by about a factor of 5 to 10. So about a factor of 10 typically. So it is much slower. That's why so far this is only for very small simulations we're focused on.
What a big price.
Yeah.
So you said you also included cosmic ray heating, so which probably is an ionization. So first of all, is it important? Second, what sets the normalization of the cosmic rays?
Yeah, so I think it
So it's
was
presumably low energy cosmic rays at
I
10
think,
to 100 MeV, right?
I think so. So what we do is basically a uniform constant cosmic ray ionization. So the parameter is the H1, neutral H1 ionization rate from cosmic rays. So this is based on the various observations. So for example, I think the one that we use is the Williams 1998 value of about 2.5 times 10 to the minus 17. And then for the other species, they're scaled to the H1 rate. And so I think it would be mostly in the cold gas, so for example the cold ISM phase where the cosmic ray heating would become important. So that the particular simulation that I showed, we also have this Jeans limit, so this equation of state. So actually, in that particular example, none of the gas was allowed to cool down to the region where the cosmic rays are likely to be important. But yeah, that's still something interesting to look at.
Thank you, Alex.